Hi everyone, welcome back to 30.100 Computational and Data-Driven Engineering. This is the Week 5 lecture video. So in the first part of the course we looked at statistics. We looked at errors and the build-up of errors, and we also looked at how we can design experiments using factorial designs and statistics, basically. Then we looked at root finding last week, and we looked at a number of different open and closed methods for root finding. This week, we're going to be looking at ways of optimizing a function. And some of the methods that we'll be using will be a little bit similar to the root finding methods that we used in the previous week. So it shouldn't be too difficult to make this jump. Then we will move on to, so this is single variable optimization. We'll also look at multiple variable optimization, optimizing a function that depends on many variables. For that, one of the methods that we used is a univariate search method. We can exploit some of these other methods, such as section searches, which is similar to bisectioning or Brent method, to slowly build up and find the optimum of multivariable problem. Now this is the fun bit. We're also going to see how this can connect to the design of experiments. The design of experiment problems that we're working on are often multi-factor or multivariable problems. So if we want to find an optimum design and we know how the design responds to these different variables, we can use some of these multivariable approaches to find the optimum design. Okay. So 1 week from now, you'll be able to determine the minimum or maximum of a function or its saddle points computationally. The sort of algorithms that you'll be using are section searches, parabolic fits, and Brent method. These will be particularly useful for the single variate or single variable problems. Some of these methods can be exploited as well in multivariate problems, multivariate unconstrained problems. And we'll also look at a few other methods, including steepest descent and Powell's method. So this part of the course makes heavy use of Chapra's book, Numerical Methods for Engineers. In particular, for today's class, we'll mainly go through chapter 13, and we'll also go through a little bit of chapter 14. So the unconstrained optimization, and we'll touch on multidimensional optimization. In the cohort classes, in the practice classes, we will also go a little bit deeper into the multi-dimensional problems. So there's one lecture video this week, that's this. There's 8 case problems, and I should have put here that there are 2 cohort classes as well for practicing. So often in engineering, we want to find the maximum of something or the minimum of something. For example, we might want to understand what conditions lead to a system's maximum efficiency. Here we have a graph of f of x, and there's a global maximum. This means it's the maximum in the whole data set and in the whole function values. And there's also a global minimum. But unfortunately, in this particular function, there are also local maxima and minima. This makes finding these peaks, or the true maximum I should say, makes it very difficult because we can confuse our program and we won't actually know whether this is the true value or not. So even though it's difficult, there are methods that we can use to find the true maximum. Probably the most obvious one is for a simple function, you could plot it and then you could just look to see the range where you might expect the maximum. You could also randomly generate guesses of x, if it's truly random, and if you do enough guesses, you might be able to find a maximum value. Or you could start at a particular, you could do some sort of search where you find a particular peak. It might be a local maximum, but instead of just sticking at that peak and saying this is the true maximum of the data of the function, you could perturb the x value slightly to see if the function changes or gets larger. In which case, in this case, if the perturbation is large enough, we'll probably find a new maximum. So there are a few techniques that we'll use for finding the maximum of a function. One is related to last week, the bracketing methods. and section searches. Parabolic interpolation, we haven't really done that in this course so far, so that will be slightly new. And then there's an open method, which is Newton's method. It's related to the Newton-Raphson method that we learned last week. Then there's hybrid methods like the Brent's algorithm. So this bracketing method is probably the most obvious way to find a maximum. It's somewhat similar to the bisection method that we learned for root finding last week. So the idea is that you define an interval, so it's a closed method, between which you expect a maximum to occur. So we define a lower bound and an upper bound. Then to understand whether a peak or a trough occurs, you need a third value. So if we add this third value here, this third point, we can tell that there's a peak between x equals L and x equals U, because the function value at this particular x value is larger than the function value at xl and the function value at xu. However, we want to reduce this range of the lower bound to upper bound. We want to reduce the search space so we can have we can know the position of this peak with more accuracy. So we can add a fourth value. So maybe we add a fourth value, in this case halfway between x equals L and x equals U. And now I know that the peak is, this peak here has a larger function value than my halfway point. So that means that the peak must have occurred in the first half of this curve, i.e. up until this point here. And it didn't obviously occur in the right-hand side of the fourth point. So we can discard the upper bound point, and this value here becomes the new upper bound. And then we can repeat the process over and over again, just as we did with the bisection method, replacing one of either the lower bound or the upper bound, so that we can slowly hone in on the peak. On the previous page, I added this fourth point at the halfway position between XL and XU, and I was able to determine that the peak was on the left-hand side of this point at the halfway position. It turns out that you can get an efficiency enhancement in how quick your code converges if the two distances from XL to this fourth point and XU to this fourth point, if they're equal to the total length of the interval, and if the ratio of L1 to the total length and L2 to the total length are equal. Basically there's an efficiency enhancement. Your code will converge faster. And if you go through the maths, we find out that the distance between XL and XU should be 61.8% of L0, the interval length. So in other words, we should split our search space in half at this point here, and then we'll have an efficiency enhancement. And this will mean that we can have a smaller number of iterations to find the peak within some specific accuracy. Now this number 61.8 is a very special number that often occurs in mathematics, in geometry, and in nature. I think in next week's class I might talk about that a little bit. But for now, you just should accept that the efficiency enhancement can occur if we choose this golden ratio as our splitting position. So if we split the interval between XU and XL 61.8% of the way across, this sectioning method is called the golden section because we're using the golden ratio, and it tends to converge very rapidly. So after 10 iterations of your algorithm, the search space will shrink, or the interval will shrink, by a factor of 0.618 to the power of 10. So it'll just become 0.8% of the initial interval that you chose. Or if you do 20 iterations, it'll become 0.066% of the interval that you initially chose. So it converges very rapidly and quickly. So let's do a quick golden section search example. Imagine we have this function 2 sine x minus x squared over 10. It looks like this. It has a peak somewhere between 0 and x equals 4. So we will say that this is our interval. The lower bound of the interval is at x equals 0 and the upper bound is at x equals 4. And we're looking for a peak somewhere in that range. So to find the peak, we should strategically use the golden ratio and select our next x value to be 61.8% of the across the interval from 0 to 4. So that turns out to be 2.472, which is this point here. And our second value that we should choose should be 61.8% of the way from 4 to our lower bound, 0. So that turns out to be 1.528, which is this position here. So now we have 4 values in 4 positions. We have the lower bound value of 0, and we have this upper bound position, which we haven't actually calculated the value of. And then we have the x1 and we have x2. Now, looking at these values of f of x2 and f of x1, we can clearly see that f of x2 is larger than f of x1. Okay, so this means that we can we know that the peak is going to be to the left of f of x1. It's going to be to the left of this point because the x2, which is a smaller value, a smaller position of x, which is to the left of x, produces a higher value. So we know the peak is going to be in this section of the graph. So we can discard the upper value of x. So x1 can become our new upper value. So our new value for the upper bound, our new boundary, our upper bound of the interval is our old x1 value. So the former x1 has become the new x upper. x2 has not changed. It's still in the same position. But we also know the lower bound position, xl, that hasn't changed. The only thing we don't have is the fourth value, x1. So we can choose that again strategically. We need to go 61.8% of the way across from xu to xl. So that turns out to be x equals 0.994, so very close to 1. And we can calculate the value of the function at x equals 0.994, and we can now see that we're kind of honing in on where the peak is. And we perform the same action again. We can see that in this case, as we go from x1 to x2, we're increasing in value. So we know that the peak cannot be between x1 and xl, so we can discard xl. And our new bounds for where the peak will be from x1 to x upper on this graph, these 3 points. And we can perform this iteratively over and over again until we find exactly where the peak is. So for this example, after the 8th iteration, we find that the maximum occurs at x equals 1.4427. And this is extremely close to the true value of the maximum of this function, which is at 1.4276. So we can see that this has only taken 8 iterations to get to the something very close to the true value. So another efficient method of finding maxima in a function is to fit a Lagrange polynomial to data points in that function. So for example, here we have this reddy brown colored function, and then we pick 3 points, x0, x1 and x2. We can then fit a Lagrange polynomial to those 3 points. And this Lagrange polynomial fit is shown by this black line in this curve here. You can see that it approximates quite well the shape of the underlying true function. And we can also see the peak of that polynomial is identified as x3 in this graph, and it's not too far from the true maximum. The reason this works so well is because usually peaks have, at least over a small scale, look like they have some sort of parabolic shape. So by fitting a parabolic function to any 3 points close to the peak, we're going to get a reasonable estimate of what where the true maximum is. So this horrible looking equation here is how you can pull out the peak of a Lagrange polynomial that's based on 3 other values, x0, x1, and x2. So if we know f of x1, f of x2, and f of x0, we can put those numbers into this equation, and this equation will output the value of the peak of the fitted polynomial, which is what we're looking for. This red curve here, this red dot here. So after finding the peak of this polynomial, we need to have a method to further converge. So we can usually do this by using the golden section method again, because now we have 4 points. So we can use the golden section method to understand which of the 4 points we're going to discard. Or we could just simply replace the oldest value, in this case it would be x0, and just fit a new polynomial to these top 3 values. Either way will work. So let's apply the parabolic method to the same equation that we used before for the golden section method, which is 2 sine x minus x squared over 10, and it's plotted here. And we will take the lower bound and the upper bound, and we'll also choose a point x1 equals 1, which is this position. So we can calculate these 3 values by plugging 0, 1, and 4 into the equation f of x, and we find the values of the function at those positions, and then we can put those values into the equation that was on the previous slide that gives us the next position of x3. So x3 turns out to be at 1.5055. So we'll add that to the graph just here. Now, because f of 1.5055 is larger than the previous x1, we can see it here. The new value that we've just calculated is larger than x1. We know that we can discard any points that we had to the left of x1. So we got rid now of x0. And we have 3 new points: x1, x1.5055, and x4. So those are 3 new points that we can fit a new polynomial to get a better estimate of where the peak is. So if we go through this process and repeat it very rapidly, the system will converge on a value of x equals 1.4276. So previously we needed around 8 iterations of the golden section method. With this parabolic method, we only need 5 iterations to get to that similar level of accuracy. So the previous 2 examples, the golden section method and the parabolic method, they're closed methods. We enclose the area where we think the peak is. Last week, for root finding, we learned about the Newton-Raphson method, which is an open method. We only have to define 1 point, and it will predict where the root of the equation is. So if you have a function f of x that has a root, if we take the derivative of f of x, we can use this approach to predict a new value of x, which should be closer to the root. In the case of optimizing, we want the first derivative of the function to go to 0, because at a turning point, the gradient of a turning point is 0. So instead, we can replace the function with the first derivative of the function, which is the thing we want to go to 0. And instead of dividing by the first derivative, we would have to divide by the second derivative. And then we could use exactly the same technique, really, that we used for Newton-Raphson method to find roots of the first derivative of the function. In other words, find the maxima or minima in the function. So the good thing about this is we don't need to put any bracketing. We can just use a single starting point, but it's not as stable and it might diverge. Also, the first and second derivatives need to be computable. Until now, we've only really been looking at finding peaks in functions that depend on one variable. Now we're going to look at methods to find peaks in functions that depend on multiple variables. Earlier in the course, we looked at fractional factorial designs, and the designs, configurations, or the experiments depended on multiple factors or multiple variables. You can build a model based on those statistical designs that depend on multiple variables or the multiple factors. The techniques that we're going to learn this week could also be used to find the optimal conditions from the model that depends on multiple factors. So there are two main approaches to finding the peaks in multivariate problems. They are the direct approaches and the gradient approaches. So the direct approach is what we're going to concentrate on in today's lecture, and then in the cohort classes next week we'll look at the gradient approaches. So a typical direct approach doesn't take any information about the local environment or how the function behaves locally. For example, a random search would be an example of a direct approach. In a random search, we'd just try lots of random values and calculate the value of the function at those random values, and then try to estimate, or we'll be able to identify which random value has the highest function value, and therefore we can say that that's probably quite close to the peak. A univariate search is something that I'm going to describe in a few moments. Then in the cohort classes, we will concentrate also on the gradient and steepest descent methods. So the random search method is a brute force approach. It's relatively slow. So if we have a function that depends on two variables, x and y, we might try different combinations randomly of x and y and see which value has a maximum. It does have a few advantages over some of the other methods. Some of the other methods, for instance, the gradient methods, rely on the function being differentiable, and the random search method doesn't. It will always give you a optimum value. Whether it's the true optimum or not depends on how many different combinations of x and y you use. But it's very inefficient, so we probably won't use this too much. So a slightly more sophisticated approach is the univariate search method. So this tries to reduce a multidimensional problem into a one-dimensional problem. So imagine if you have this two-dimensional surface here, and we want to find the peak of this surface, which is at this point here. What we could do is start at position 1 and choose a direction, either x or y. So let's move in the x direction. As we move across, we eventually see a rise in the function's value. So we'll see a rise and then a fall, so that the function will create some sort of peak. Because there's a peak in the x direction, we can we can use one of the one-dimensional search methods that were described earlier to find where the peak position is. In this case, it's at position 2 here. Once we're at position 2, we move in the orthogonal direction. So we move in the y direction and do exactly the same thing. So we're at position 2, and as we move upwards, we eventually hit this new contour, which indicates a slightly higher value of the function, and we'll see a peak. And as we go back down, the peak will become quite obvious. So again, now we use the one-dimensional searching methods to find position number 3. Then we move orthogonally again, and then again, and again, and again. And eventually, we zigzag across, we'll get to the very peak of the function. So this is a way of changing a multidimensional problem into lots of small univariate problems. So a third technique to find the peak of a multivariate problem is Powell's method. It is an extremely efficient method, and it works by initially defining a starting point, which is not too far from the peak, and 2 vectors, h1 and h2. We scan along the first vector, along the direction of the first vector until we hit a peak in a one-dimensional scan. This becomes our next point, and we've labeled it position 1 here. At position 1, we choose the second vector, h2, and we scan in the direction of h2 and do a one-dimensional search. And then we get a new position. Now the vector that connects h1 and h2 is it points towards the peak of the multivariate problem, of the multivariate function. And this becomes our third vector, h3. So h3, as you can see, is starting to point towards the peak of this multivariate problem. Then we go back 1 and we reuse the previous vector, in this case h2. So we scan in the h2 direction, and until we see a peak again. And once we find that peak, we use the previous vector, which is h3, and scan in that direction, do a univariate search. And those 2 vectors combined gives a new direction, which we call h4. And h4 is now pointing towards the peak. This is a very efficient method, especially for quadratic problems, and scales very efficiently. So that pretty much summarizes the lecture that I wanted to give this week. We've looked at one-dimensional search methods for optima and minima, or saddle points. So in particular, we looked at the sectioning methods, parabolic fits. We haven't looked at Brent's method, but we will do in the cohort class. And then finally, we looked at how to optimize single and multivariate functions, implementing kind of univariate searches and Powell's method, and also random searches, which isn't listed here. In the cohort classes next week, we'll also apply the steepest ascent methods. So thank you very much, and see you next week.